So are you able to see the screen?
Yes, sir.
Yes, sir. Good morning, sir.
Morning, morning. So we will be starting last two topics of our this unit 2, which is part of what we call as statistics. So it is maximum likelihood estimation. I will of course give you the problem description. I will discuss it, and hypothesis testing. So these are the two topics which we are going to do next. Before proceeding with that, of course, what do we understand by statistics? I mean, by this time, all of you must have heard probability and statistics together. Can anybody help me figuring out the role of probability and statistics? Why do we call these two different topics and what is it meant about? Anybody, anything, whatever you know of. I mean, we use probability and statistics as our unit. So when we say quantum mechanics is probabilistic in nature and quantum mechanics is statistical in nature, what do you think it means? Okay, so let me just give you an idea. I am audible, right?
Yes, sir.
Okay, so let me
Yes.
just
Yes, sir.
give you an idea that there exists something what we call as population, which is in a large sense about whatever about which we want to know, and there exists something about a sample. So it is the relationship of the population and the sample, which is what is basically governed by these two aspects. So for example, if I tell you that there is a pack of cards, playing cards, and then I ask a question, what is the probability that a randomly selected card is a red card or a card of a spade or a card having two? So what we already know that there exists 52 cards in this deck, and then we also know how the red and the black cards are there. So the overall idea about the population is clear. The question is specifically for the next some event or for some sample. When we already know things about the population and we try to predict something about sample or a given event, this arrow is what governs what we call as the probability. In fact, if you figure out that in probability, we are always asking questions like, what is the probability that an electron reaches a screen at a particular position, given it has passed through, for example, a double slit experiment? On the other hand, the reverse question that we want to know something about the population, but there is no way to figure out everything about it. Can we can we draw a sample and from that we can predict things about the population? Can you please mute? Can all of you please mute? Thank you. So this portion where we have some idea of the sample, but we do not know much about the population, either the parameter or something else, and we are trying to predict or estimate some population related item from a given sample, that comes under this statistics branch. So statistics is mainly on the portion of having a sample, and from that sample we can try to predict something about the population. Whereas the population goes, of course, in the opposite direction, and they of course are governed by laws of probability, those which we have studied. And that's why, since they are governed by the laws of probability, that's why we basically deal about them together. Yeah, so that's the, of course, portion of the statistics. We do not know something about the population and we try to infer it from the sample. Now, statistics in general, they are actually useful for two aspects. One is what we call as the parameter estimation, and I will quickly come to that. I'm still building my problem, or in general what the problems are. And another is about the decision making. So the two topics, maximum likelihood estimator and hypothesis testing, fall under these two broad topics, parameter estimation and decision making, respectively. Now, what is parameter estimation? Parameter estimation is something like this. We discussed during our probability mass function or probability density function that there exist not only random variables, let's say x, y, z, but there also exist certain parameters of a distribution. So for example, binomial distribution has n and small p as the two parameters. Poisson distribution has lambda as the parameter. Gaussian distribution has mean mu and sigma, standard deviation or variance sigma square, as the population or as the parameter. So whenever we talk about a PDF, we talk about not only the random variable, but we also need to know about the parameter. So when we are saying something parameter estimation, what we are saying is somehow we do not know about this parameter, population parameter true value is not known, is not known. And we want to estimate it from our sample. This comes under our first topic of maximum likelihood estimator or maximum likelihood estimation. So the topic which we are going to take care of, MLE, maximum likelihood estimation, that topic deals with the unknown true value of the population parameter, and we are going to figure it out from the sample, whatever data we have taken. So this is what we call as the parameter estimation. Okay. And we will see in our next topic how, by having some idea of that, we can also make decision. And I will of course discuss about it further. So our first topic deals with the branch of statistics, which is about estimating a population parameter which is not known. So this is the broad introduction to the topic. I will of course now come to the basics of that in terms of the maximum likelihood estimation. Any questions on the broad discussion? Oh, okay, fine. Yes.
Do we have only the MLE for the parameter estimation?
Yeah, that's a good question. So there are several methods. Actually, I mean, one can think of. One is that we are trying to predict about the population from the sample. So there should be some way that I can use my sample values to predict the parameter. Maximum likelihood estimation is not the only method. There are other methods called method of movements. For example, even our famous curve fitting or the linear least square is the method, although it is intimately linked with maximum likelihood estimator. There is reason why we choose the maximum likelihood estimator. I wouldn't directly go into that detail immediately, but I will tell you just briefly. We will not do the mathematics, but I will tell you briefly that what makes the maximum likelihood estimator a reasonable choice or a very good choice for parameter estimation. So there are several methods, but maximum likelihood is one of the most attractive one. Anybody else?
Okay, sir.
So, okay. So what we will tell in the next true value points that let's say there exists some true value which is value of the population, and of course this we do not know. Yeah, not known. We will build our estimator which we will put as the theta cap or theta hat. And then we will use this estimator to make an estimate. Sounds all abstract, but it will soon be clear. And we will have an estimate which will reflect the true value. This is what we are saying. Now, it doesn't mean that, of course, the estimate is the correct true value or not. There will be some error which will be associated with that as well. However, that's the best we can do. This is what we will say. So now giving you a specific example. So again, this example is coming from the nuclear physics experiments, but of course it can come from anywhere else also. Now, let's say you are doing a counting statistics experiment and you have a source given to you. So one question which comes quickly is that source gives you counts, and the counting statistics is governed by what we know as the Poisson statistics, right? And we also know that for the Poisson statistics, the PDF is given by, or is it PDF or something else? What do we call this? This Px lambda, what do we call this?
PMF, sir.
PMF, probability mass function. And why do we call it PMF?
Because this is
Because of discrete function.
Because our random variable is going to take only discrete values, and for the discrete values we talk of what we call as the PMF. Yeah, okay. Now we know that our counting statistics is governed by this Poisson distribution, for which the PMF is given like this. This is what we already know. However, when you are going to conduct an experiment, you do not know what value you are going to give to lambda, which is a parameter. And you want to figure out somehow that there should be some way that I can think about lambda. Either somebody gives that value to you, or otherwise you are going to get that value from this population. But you cannot study the entire population. So what you are going to do? You are going to do an experiment. Let's say, for example, that you are going to fix the preset time to some value, and then you are going to take values for various, I mean, for the same preset value, several iteration of that. And you may get x1, x2, x3, x4, so on and so on. Yeah. So somehow you will have to use these values to predict this population parameter. That's what the question is about. A specific question now is about that we know that our source is described by Poisson statistics, or the counting statistics is described by the Poisson statistics, but we do not know what is the value of this parameter lambda, which is for the population. If somehow I can study the entire population, then will be good, but you cannot study the entire population. That means all the possible decays of that particular source throughout whatever infinite times. That we cannot do. So we are going to estimate the unknown value, unknown true value from these xi, xn. This is what we are going to do. Fine. And what do? We are going to use the one law of probability and statistics. And what's those law? We say that each of the value which we are getting, they are basically corresponding to random variables which are identically and independently distributed. So each of the value which you are going to have, so for the 2-second experiment, one value you have got, that value actually corresponds to some random variable x, which is distributed according to which distribution? Now this x, since you have now taking the sample from this Poisson statistics one. So this random variable will be distributed according to which distribution?
Is it Poisson distribution?
Poisson distribution.
What else it can be? Remember, the counting statistics tells you that you have this distribution, which is the Poisson distribution. So if you take value anytime, that value should be what? That value should be one of the random variable x1, which is nothing but which is distributed according to, sorry, x1 distributed according to the same Poisson PMF. If you take the second value, which is of course independent of the first one, that is the reason why second I, that is also distributed according to the Poisson distribution. Third value which you are going to take, that is also distributed according to the Poisson distributed. Any value which you are going to take from this, that's distributed according to the Poisson distribution. So if you are going to take n values, each one of them corresponds to a random variable. So remember, whenever I write capital letters, it corresponds to the random variable. And wherever I write a small variable, that means that it has taken some value. So these values correspond to the random variable, which are all identically and independently distributed according to Poisson PMF. That's the first thing we say. So that means that the sample which we are taking is somehow a random sample or a sample corresponding to this distribution. Okay, so what do we do next? What we do next is, once I know that, I can quickly write down my joint PMF. What will be the joint PDF of these observations?
Sir, product of all these distribution.
So why did you say product and why didn't you say that it will be joint? I mean, why
So
did you
it
say
is
that?
not,
They are
Because all are
independent.
it is independent, sir. Identically
So
independent.
they are independent.
They are independent. Very good. So they are independent, identically distributed. So it can be written from the laws of probability that it can be written as the product of these. Right? So I can even write down this. Y exponential minus lambda, lambda raised to power x over x factorial. So this is xi, this is xi factorial, I going from 1 to n. Yeah, this is all good. Before we conduct the experiment, our joint PDF comes like this. What once we conduct the experiment? So let's say you have actually taken the value. So after you conduct the experiment, what will happen after you conduct the experiment? So joint PDF describes what? Joint PDF just describes that the probability your random variable can take any value will be given by this. After you conduct the experiment, that means that the random variable x1 has actually got the value. So theoretically, it means just this. Each of the random variable which you have got has got these values, which means your x1, x2, xn are all fixed. Now these xi's, which were random variables before conducting the experiment, after you conduct the experiment, they have got the value. You have really got the values. So they are no longer remained random. They have now been fixed. So what is it which is not yet fixed in the whole formula?
lambda.
Lambda.
So lambda is not fixed, and this is what the idea behind having it. So we call the same joint PDF, what we describe as this formula. After we conduct the experiment, we call this a likelihood function. We call the same thing. It is just the interpretation which is different. So now we call the same joint PDF as the likelihood function because the values of xi's are all fixed and lambda, that is the parameter of the population, is the only unknown. So see that the difference lies only in terms of the interpretation of the same function. Before the experiment, xi's are not known, lambda is not known. But after you conduct the experiment, your xi's are all not now known. So the same function we call as the likelihood function, and we write exactly the same formula, except knowing that these xi's, etc., they have all got some values. So that the same function is now the function of the unknown variable, unknown true value of the population parameter. So the question comes, how to get the value of this lambda? And there lies this concept that we are going to find out the value of lambda which maximizes the likelihood function. So this is all about the maximum likelihood, that we are going to get the value of lambda which maximizes the likelihood. Because when we are going to maximize this likelihood, it will mean that our observed data will give the best or estimate of our parameter. This is all it means. When we talk about the maximum likelihood function, the first question is what is likelihood, and then the second point is how to maximize the likelihood. Now, in certain cases, of course, you may not have a function which can be simply, I mean, in general, how do you maximize, by the way, a function? How to maximize?
So by taking
By
its
simply
derivative
taking
and
the
equating it to
differentiation.
0.
Right. In general, if L lambda is differentiable, then of course it is rather simple. This is what generally we do. So dl lambda over d lambda equal to 0 for a specific choice. This specific choice is called the estimator. And of course, since it's maximization, so what will happen to this? At lambda is equal to this.
Must be less than 0.
Less
So
than
this
0.
should be less than 0. Yeah. So this is all we have to do. And generally, instead of maximizing d of likelihood, what we do is we maximize the log likelihood. So what does that mean? I am going to do d of d lambda of log lambda equal to 0. Why I would like to do it? It is rather simple from the previous page. As you can see that the likelihood function is the product of so many terms. So if you take the log, what will happen? If it is a product of many terms, if you take
It
the
will
log,
become sum.
so the log
Sum of
will,
all
right,
individual
right,
logs.
the product will convert into log of, sum of log of those. And if it is sum of log of those, that means taking the differentiation will be easy, because now you are not going to take the differentiation or derivative with respect to product of many functions, but with respect to sum of many functions. And it is always easier to do that. The one question, of course, you may ask, sir, am I justified in taking log? I mean, is it always doable? Can I always use this? That whenever I have to maximize L, can I always maximize this d over d lambda log L? Can we? So what is in general, if I take d of d lambda log, sorry, log lambda L, what does this mean? What does this mean? Taking d of d lambda of log of L? Can you just do that simple derivative? What will be the d of d lambda of log of L?
1 by L del L to del lambda.
1 over L dl over d lambda. Very good. Now, can I always do this? Question. I can always do this if I know something about this guy L. if this is positive and if it is greater than 0. Then you can of course always do that. So instead of equating d of L over d lambda equal to 0, you can do 1 over L d L over d lambda equal to 0, because you know your L is always positive and L is greater than 0. But is L positive and L greater than 0? What is L? What is likelihood?
Yes, it is positive.
Since likelihood, yes. Why are you saying that?
Probabilities.
Yeah, this is it. It is, remember that likelihood function is just the interpretation of the same joint PDF after we conduct the experiment. So likelihood function is basically obeying all the laws which our joint PDF will be obeying. And what is the law which joint PDF obeys? Joint PDF says that, of course, it has to be positive. It's just that for exactly equal to 0, this thing may not work, but exactly equal to 0 is basically somehow you will see that's not even there. It will be 0 exactly at x tends to infinity, and nowhere else it will be 0. So that means our likelihood function, since it is nothing but a joint PDF, is always positive, and hence we are justified in doing it. You cannot arbitrarily decide to maximize the likelihood. We decide to do it because we know that likelihood is nothing but the joint PDF. And then rest is rather simple. Once you do it, take the derivative, take the result, whatever comes, and get the value. So let's just do this problem and try to dissect this question further. After finishing that problem, I will of course ask you, let you ask questions, but after finishing the problem. So coming back to our original problem, question is find the maximum likelihood estimator lambda of the Poisson distribution. So when this comes, then the question is mainly about that we do not know something about the population parameter and we are trying to build an estimator. So step number 1, we will write down our likelihood, which we have already done. So pi exponential minus lambda, lambda raised to power xi factorial, where I goes from 1 to n. Step number 2, build log of L lambda. So what will be log? By the way, can you simplify this product? What will be the term exponential minus lambda multiplied n times? So this is something this, in case if someone has difficulty in reading the product, so this will x1 factorial e minus lambda x2 over x2 factorial, so on and so forth, e minus lambda xn over xn factorial. This is all it is. So what will be this reduced to? E minus lambda multiplied n times?
E to the power minus n lambda.
E to the power minus n lambda. What will be this? Lambda x1, lambda x2 up to lambda xn? Lambda raised to power summation xi, where I goes from 1 to n, and divide by, now you cannot do much. You will have to, of course, write xi factorial product. There is no other way you can simplify it further. So this is I is equal to 1 to n. And of course, here also is the same. So what is log of L lambda then for this term? So if you take the log of this quantity, the whole one. So log of first
minus
term,
n lambda.
okay, minus n lambda, then
Plus summation
Plus
of
Plus summation
xn.
xi L lambda.
xi
log of,
lambda
very good. Oh, sorry, log of lambda
minus
right. minus
sigma bracket sigma, sir.
okay, minus bracket sigma I, okay,
Xi.
xi or log of xi? So what will be this? Log of x1
The log of
factorial, x2 factorial, so on and so forth, xn factorial. This will be what? You will say
Log
log of x1 factorial plus log of x2 factorial, so on and so forth. That means this will be summation log of
okay,
xi
okay, sir.
factor,
Okay, sir.
right? So
Yes,
minus
sir.
I, absolutely right. Log of xi factorial. Although this term looks very complicated, but you do not need to worry about it. Why? Because the next step is we are going to take d of log L lambda over d lambda. What will be this?
minus n plus
Minus
Minus
n
n
plus
plus
1 upon lambda summation 1 upon
summation
lambda
xi
summation xi.
and anything else?
No,
Third.
sir.
Oh, so
No, sir.
maximum. So let's just maximize it. So maximization means that just take lambda equal to lambda this whole term will be equal to 0. So this implies minus n plus summation xi over lambda this guy carried. So for this particular value of this lambda, we have d log of L over d lambda going to 0, which is okay, one of the extremum. We still need to say that it is going to be the maximum, but this is what we are going to do. So what will be the result? That means
summation over xi over n.
so summation over xi over and which is nothing but
Mean.
Mean.
mean. So if you take n values, what you are saying that if you are going to use the mean to estimate the population parameter lambda, then that is what the maximum likelihood estimator. So when you are using mean, for example, in your problems to say that it reflects the true value or the mean value of the parameter lambda, then that is nothing but the maximum likelihood estimator. In fact, you can do a quick check whether it is a maximization or not. So do the d square over d lambda square also.
Minus sigma xi upon lambda square.
So d square log of L over d lambda square minus sigma xi over
Lambda square.
lambda square at the estimate value, for example. Now lambda, remember summation xi is a Poisson distributed variable and xi can only take the values which are
Positive.
Positive.
0 or positive, right? That means that the numerator, this portion is positive, and anyway it is lambda square, which is always going to be positive, whatever number you are going to get, and we know it is going to be positive as well. So this guy minus is of course going to be less than 0, and the value which you have got this is what we call as the maximum likelihood estimator of the parameter lambda. In fact, this is what you are doing in your experiment. Now, think about it. What are you doing in your counting statistics experiment? When you take the counts for a given preset time, let's say a minute or a 2 minute, whatever counts you get, you say if you take only one reading, then that count reflects the mean of Poisson and root n reflects the standard deviation of Poisson. This is what you have been doing, right? Now, if you take more than one reading, say 2 reading, 3 readings, so on and so forth, then how will you get the mean of the Poisson, which is nothing but the parameter? Then you will say, okay, n1 plus n2 plus so on and so forth. So if you have taken, let's say, n values, then this reflects the true value of so this guy reflects the true value of our population. This is how we build an estimator. We are building the estimator from the sample. As you change the value of the sample, of course, your value of this lambda also changes. But whatever you get will be the best value which you can observe for this true parameter value, which is otherwise unknown. And this is mainly about the maximum likelihood estimation. That maximum likelihood estimation estimates, as the name suggests, estimates the true value, which is generally unknown, of the population parameter by maximizing the likelihood function. So each word, maximum likelihood function or maximum likelihood estimator, each of this word has to be understood. Once the word, each of these word is understood, then you understand what is the questions. I will invite questions at this point of time before taking one more problem.
Sir,
Yes.
in our counting statistics experiments, we are writing something like we can estimate the mean of the parent distribution as the mean of the sample distribution that we got from experiment. Was it, is that something like this? Is this what we're doing?
So there are two things. There are two things. One is when you took the reading, n1, for example, just single count n, what to do with this n? Why did you take this n? So first question is this, yeah? And that's what you are answering at this point of time, that when you get a single reading of n, then this single reading best estimates the true value of the parameter. So theory, experiment. Now theory says that the counting statistics has this, comes from this Poisson distribution. But theory says that I do not know what is lambda. In experiment, you basically sample from this whole population, that means from the whole source, you take one reading and you get this value of n. How to build lambda, which is not known, from this n is the question which estimator is trying to answer. What do you do with n? In this case, since you have taken one reading, so your lambda is nothing but this. But in case if you have taken, say, many of these readings, so you have n1, n2, n3, so on and so forth, how will you build something out of it which will reflect the unknown parameter value of the population? And this is what right now our estimator has said, that you use maximum likelihood estimation technique, and that technique is telling you that if you build n bar, which is n plus n3 divide by n, then that reflects this lambda best. This is this question which we have answered. Fine. So maximum likelihood estimator is just about how to get an from the experiment, which is nothing but a sample of the overall population, how to understand this. Now there is a second part of it which comes from the question which you asked, that comes from the CLT. What was CLT? Can somebody remind me? Central limit theorem.
Sir, if we have a number of random variables, then the mean of those random variables will tend towards a normal distribution.
Yeah, what it tells is absolutely right, that this n bar will tends towards the true value. So whatever you are estimating, if you take infinite reading, for example, I mean theoretically saying infinite, but very large number of readings, then this guy n bar tends towards lambda with normal distribution. So let me just write down. If n bar is normal, then you have to give me two values. One is mean, another is variance. So what is mean and what is variance? If n tends to infinity, what is mean for this particular question? It is nothing but the expectation value of x. So what is that in the Poisson distribution?
Lambda.
So this guy should be lambda. And what is this sigma square?
So lambda.
So lambda or something else? It is, remember, n identically and independently distributed. Think about it. Each one of these will get what? Each of n1. So this guy is distributed with some sigma square, sigma square. This is what we did. And these. So if I ask you to find out sigma square of n bar, what is that?
By n square.
By n square or something else? Okay. So this should be sigma square over
N.
and this is very important. Please do not forget this. This is also one of the reasons why we were doing it. So this will become what then? Lambda over n. In a single reading, please understand the variance is nothing but lambda itself. But if you take n readings, then this is divided by small n. So this is what the advantage of CLT, central limit theorem, that if you are taking large enough readings, then your mean tends towards the population mean, and the variance which it has is this n factor which is dividing. So is so this n bar tends towards lambda, and this width which is now given by lambda over n. Please go back and look into it. But this is another important point, that if you increase the number, if this n tends to infinity, then the width of course starts becoming very small. That means that the probability that this n bar is becoming equal to lambda is more and more true, or more larger and larger value, such that for n tends to infinity, this will become basically n bar will be equal to lambda. Yeah. So there are two things which are happening in this experiment which you are doing. I said that the maximum likelihood estimator is helping you to build an estimator which will tend towards the true value. Fine. And the central limit theorem tells you that that estimator which you are building is generally going to behave in the manner in which we have, of course, written here as the n bar. So am I clear in the response which I have given?
Yes, sir.
Okay. Anybody else? On the maximum likelihood estimator, I know, I mean, the central limit theorem, you will keep on thinking about it. So look into it, what we have done. Our problem was to estimate parameter, population parameter, and the methodology we use, is what we call as the maximum likelihood, where we did nothing but we call likelihood function, the function which is nothing but a joint PDF. And this joint PDF and likelihood function are different only in the sense that we are interpreting it differently. Before conducting the experiment, we call that joint PDF because we did not get the random variable any value. But after you conduct the experiment, of course, all the values are with you. And hence the function, likelihood function, is a function of only one parameter, or the parameters, other parameters. I mean, in case if there are two parameters like this question, then there will be two parameters. Okay, so let me just do next problem related with this and ask you question. Fine, question number 2. MLE of exponential distribution. Which means what? Can somebody tell me what is the exponential distribution? Is it the PDF or the PMF which I'm writing? Exponential distribution. So let me write it down and then let me ask you a question. Okay, just by looking at this, what I have written. Have I written a PDF or a PMF?
It's a
PDF.
PDF.
It's a PDF, absolutely right. That means exponential distribution is a continuous distribution which will take any value for x greater than equal to 0, any real number. Yeah, and mu is one parameter here. There is no other parameter on which it depends, and you can also see that this mu which is coming in the, the numerator or the multiplication coefficient, this guy is nothing but a normalization coefficient which you will get by integrating this PDF from 0 to infinity and get 1. So let's say you are doing an experiment which is distributed by exponential distribution. Do you know of any situation where a physical experiment is distributed according to exponential distribution? Any experiment? So how radioactive decay law is distributed? What is radioactive decay law?
Equals to n naught e power minus lambda t.
So e to the minus lambda t. Yeah. And what does this signify? What is n? What is n naught? What is lambda?
The number of remaining nuclei, and naught is the initial activity or initial number of nuclei available.
Okay.
Lambda is the time parameter, or we can let it to be half-life 0.693 upon lambda.
Okay, so somehow you know that this is related. This is a decay constant, and it is related with the average half-life. I will always use this word, but anyway. So good. So you know, see, you know that there exist distributions which follow this exponential distribution. Yeah. So somehow, if I am taking a sample from that, so if I am interested in figuring out the parameter of an exponential distribution, and let's say I have taken a sample x1, x2, xn. What will you do with these x1, xn, xn to build this mu? Because this mu is the unknown population parameter. You have conducted an experiment and you have got x1 to xn, x1 to xn. What will you do before doing x1 likelihood? Let's just think about it. क्या करोगे भाई आप? पिछली बार तो n को हमने लैम्डा कह दिया था जो कि पॉइसन वाले में. अब एक्सपोनेंशियल में आपको क्या लगता है क्या आएगा रिजल्ट? कुछ सोच सकते हैं? कुछ भी. रेडियोएक्टिव डिके लॉ है ना, तो वो तो डिके लॉ फॉलो करेगा. सो व्हाट आर वी सेइंग? एट डिफरेंट टाइम, सो इफ आई एम टेकिंग दिस रीडिंग एट डिफरेंट टाइम, आपने तो प्रीसेट टाइम लेके उसे बार बार रिजल्ट किया ना, पर ऐसा ना करें. अगर मान लीजिए किसी के हाफ लाइफ ईयर्स में है, तो मैं हर महीने रीडिंग ले रहा हूँ. एक महीने में एक रीडिंग ली, देन दूसरे महीने में दूसरी रीडिंग ली. सो आई गेट these numbers which is nothing but distributed, which is exponentially distributed. तो मेरे पास ये numbers आ गए. अब मुझे उसका mu पता करना है which is related with decay constant, let's say. तो मैं क्या करूं इन numbers का? वो जो x1, x2, xn आए, ये जो आए, इनका क्या करूं कि ये mu बन जाए? कोई guess? Let's just play the game. Summation xi over n.
Yes.
Okay. So this is precisely the problem we are trying to answer. Remember, beforehand, we do not know what to do with that. So we are going to answer this question exactly in the manner in which we did. And the reason I chose exponential, because last time I chose my discrete distribution, this time I have chosen a continuous distribution. Right? And the whole idea remains same. Since you are taking sample, so what will be first step? Likelihood function. This will be mu e minus mu x1, then mu e minus mu x2, mu e minus mu x3. So mu e minus mu xi, right? What will be this? That means multiplying mu n times.
Mu power
E to power
n.
n.
And what about the next one? Exponential minus mu summation xi. It's rather simple. What is our step 2? Just take log of L mu, and this will become n log mu minus mu summation xi. Let's do the maximization. D of log L over d mu, mu is equal to estimate equal to 0. So what will be this? N over mu minus summation xi equal to 0. And the result of mu will be
Summation
N
xi
over
over n.
summation over x.
n over summation
N over
xi. Right. N over summation xi. So now you know what to do with your values x1, x2 to xn which you have got. All you have to do is to put just those in the denominator and divide it by n. So it is basically, if you look into it, it is nothing but 1 over x bar. This is what you should do to find out your mean in the exponential distribution. And that's what the power of maximum likelihood, that once you take the reading, how to get an estimate of this unknown parameter. This is what the maximum likelihood is doing for you. Okay, so that's what I wanted to show. I mean, you can take d square L over d mu square also. What will be the result of that? Where is it a maxima or a minima?
Maxima.
It is maxima because your mu where x is greater than equal to 0, and anyway you will have mu square in the denominator, right? So minus
Yes.
n over mu
Yes.
square. Minus n over mu square. Mu square is of course always going to be positive. N is a positive number of readings you are taking. So this is of course a maxima, and that means it's a maximum likelihood estimation of this. So again, remember the question which you are trying to answer. The question which we are trying to answer is, we did not know this population parameter and we are trying to estimate. And while estimating, we will of course rely on the data which we have taken, because that is the best, that is what is going to give the best estimate of this true value. And that's what precisely we are doing in this likelihood method. And we are using the law of probability, that is, we are understanding that there exists a joint PDF for identically and independently drawn portions, and we can just use that to build our likelihood function. Questions on this point? Okay, so let me give you a homework question in that case. Find MLE, maximum likelihood estimate, of both mu and is of Gaussian distribution. Fine. Remember, your Gaussian distribution is described by 1 over root 2 pi sigma square exponential minus x minus mu square over 2 sigma square minus infinity less than x less than infinity minus infinity less than mu less than infinity. Sigma is always, sorry, greater than 0. Yeah, greater. So equal to 0, it's a delta function. We'll not talk about that. So here there are two parameters which are not known. What will you do in that case when there are two parameters which are unknown? How are you going to work on that? So you will build your L, step 1. Step 2, build your log of L. Now step 3, we have been taking d of L over d of the parameter. Now there are two parameters which are unknown. So you will have an equation where we will say this guy equal to 0, and we also said and this guy is equal to 0. That means you will take derivative with respect to both the parameters, and you will have two simultaneous equations to solve. So you will solve for two simultaneous equations and get the values of mu n. Fine. So instead of having one equation, you will have two simultaneous equations. Let me just tell you the problems which I have seen over the past, which students do while they are attempting the same question in the examination. Several students start, instead of writing the product of many terms, they start just by saying that, okay, we are starting with one term only, that is mu e minus mu x, instead of saying that we start with the sample, which in some sense is wrong, because what we are saying is that we will start with by taking samples. So always build your L mu as the product. Now product is, since they are independently drawn, you can write down this product. There is nothing wrong in that. Yeah. Second thing which I have seen, that equal to 0 happens only for this estimate. So when we are saying that log of L is maximized, this is maximized for this mu is equal to mu caret. You cannot just write, for example, in this second equation, n log of mu and then caret minus mu caret summation xi. The particular value of mu for which that d of log L of d mu is equal to 0 is what we call as the mu caret or mu hat. So please understand that our mu hat is the estimator here, which when you are taking the value of xi, they will become nothing but the actual value, which will reflect the true value. So this is generally what I have seen while checking the papers, that students tend to miss their products or tend to miss their, I mean, mu hat they are putting almost everywhere. They cannot do that, because then the concept is not clear yet, it seems like. And I should of course leave you with the food for thought. And what would be the food for thought? First food for thought, if function is not differentiable, what will you do?
So then we'll not take the log, we'll directly take the derivative.
Yeah, you still do something interesting, but what I mean, you cannot take the derivative. That's the idea. If the derivative cannot be taken, that means that it is immaterial whether you are taking log or not. That means that there is no simple closed form or analytical formula for taking the derivative. What if the derivative is not there? Question number 1. And question number 2. So what if L is derivable? Question number 2. Somebody asked a very simple question in the beginning, sir, is maximum likelihood estimate the only method to estimate? And I said, no, there exist several methods. Okay, so then how to decide if MLE is the best estimator for you? This is, of course, I mean, there first question I can still think about from the syllabus point of view, because you can at least think on that. Second question, I wouldn't say that that qualifies to be from the syllabus point of view, because that requires you to think about it something more. What will you think is what I am interested in knowing, because this is something that maximum likelihood doesn't end here. And the final thing which I wanted to say about the maximum likelihood in this class, remind me what was the estimator which I built for Poisson? Remind me that. शुरू में हमने क्लास में किया था ना? Example number 1.
Sir, sigma xi by n.
Summation xi over n. This
Mean
was
of
equal x bar. Now look at this estimator before experiment, before conducting the experiment. This lambda is what? Random variable 1 plus random variable 2 plus random variable 1 xn over xn. Yeah. So each one of these guys x1, x2, xn, they were random variable. After we conduct the experiment, what happens that each of these guys having some value, and that means that you are getting a fixed value. So this is what I call as the estimate, and this is what I call an estimator. Estimator is something which we have built. I mean, you can actually build without even performing an experiment, but a particular value you are going to get, when you perform an experiment. If you repeat the experiment, are you going to get the same value or are you going to get the different value? So you have performed, you know your estimator, this is what you are going to build. You perform your experiment once. That means you have taken, let's say 10 readings, and you have taken this 10 average with respect to 10. That's what you have done. That's the estimate you have got. If I repeat the experiment, that means I again take the 10 values and I divide by 10. Are we going to get the same value or different?
So different, I think.
Different value.
I think different, or we will get different. I mean, it's a very, very, very unlikely coincidence that you are going to get the same value. Very unlikely coincidence. But yeah, I mean, generally you are going to get different value. So what does that mean? That means that this lambda, what we are building here, this guy will also have some distribution. Right? I mean, the lambda what we are building, the estimator what we are building is going to have distribution. If you keep on performing the different experiment, you will keep on getting different values. That also tells you that this, whatever we are building, it is also a random variable. This is of course clear from the first point also. When I am writing lambda hat is equal to capital X1 plus capital X2 plus capital Xn, you already know now. If there are random variables x1, x2, xn, sum of the random variable is also a random variable. Yeah. So this guy will also have its distribution. This guy will also have its width. Something which one needs to just remember, that one actually thinks about my question number 2 in this manner, that if somehow I can know the width of the distribution which I am getting from maximum likelihood estimator and which I am getting from several other estimators, then I can compare this width to see which has the lowest width or the smallest width. And then I would be able to zero in on which of the estimator I should use. So this is, I have given you as a food of thought. That means that that will require some further understanding. But what I want to emphasize here, that the lambda which we have got as an estimate value, if you think about it just before conducting an experiment or otherwise, it is also a random variable which will have its own distribution. And that distribution can be used to do some further analysis. We are not going to do it. We will stop here, that we should be maximizing our likelihood, and just done with that. So questions on that, or otherwise I will just finish it off. I will request all of you to please connect in my additional class today, because there I will start discussing about the decision making portion, which is what falls under the hypothesis testing. It's not only about a question which I asked in my last class, central limit theorem, and I asked you to find out probability of head for a particular case. I will start by discussing that first. So initially I will build on that, and then more discussion on CLT, and then I will start with the decision making. Fine. So questions. No further questions. Okay.